So you should be able now to see my screen. I slightly changed the scope of my topic. I will give you a kind of overview of the many different theories to treat collective spontaneous emission in order to really have a quantitative comparison of theory and our recent experiments. I would like to thank my two colleagues, Andrei Benediktovic and Stasis Čučurka, who are working on the theory side of this project. And the experiments, have been involving several more people, but the main players at the experimental side are Laurent Mercadier, Jose Crespo, and Daniela Rupp. So we had the theoretical work was mainly encouraged by a series of experiments that we have been conducting in the last 10 years at free electron lasers, where we irradiated optically thick samples, mostly gas phase samples, but recently also solids and liquids. We irradiated them with highly focused FEL pulses of a few femtosecond durations, and looked into laser-like emission out of these irradiated atoms. And we're trying to understand phenomena of amplified spontaneous emission, superfluorescence, and inertial X-ray lasing. And here you can see a typical outcome of such experiment. This was there are two experimental campaigns at Flash free electron laser in Hamburg, where we irradiated xenon atoms. We focused FEL pulses that have been tuned above the 4D ionization edge of xenon. And in a macroscopic ensemble of atoms, created a population inversion in xenon 2+ ions. And we observed several strong laser-like emission lines containing something like 10 to the 6 or 10 to the 7 photons in each emission line. And you see here as a function the emission yield, the number of detected photons as a function of FEL pulse energy. So by increasing the pulse energy by a factor of 3, we actually have 3 to 4 orders of magnitude higher signal strength. So it's quite impressive phenomenon. And if you switch from gas phase to clusters, decoherence in the system starts to play a significant role. Most of you know that if we irradiate clusters with high intensity pulses, we're creating a nanoplasma that evolves on a picosecond, femtosecond to actually nanosecond time range. And these collisions in this nanoplasma then really alter the population dynamics of the system. And you see that the cluster emission is several order of magnitudes lower. And we wanted to have a theoretical approach that would be able to describe both of these systems, or at least these decoherent systems or highly coherent emissions on equal footing. In other words, we want to have an approach that goes from amplified spontaneous emission to superfluorescence and superradiance within one coherent approach. So this concept of collective spontaneous emission and superradiance was introduced in 1954 by Dicke, and then it was a quite academic paper where he considered an ensemble of atoms that have been regional in space, small compared to the emission wavelength of these two-level atoms. And he started out with these atoms in a very symmetric state of excited atoms. So all of these N atoms are in an excited state. And then at some point in time, one of these atoms would decay. And since these atoms are indistinguishable, the state following the decay is a highly symmetric state. That's a coherent superposition of states that can be characterized by N-1 atoms in the excited level and one atom that is in the ground state. And he showed by an angular momentum algebra, the states can, this highly symmetric decay states can be mapped to this angular momentum algebra, that the emission characteristics of this ensemble of our states is very different to the usual Wigner-Weisskopf decay, so this exponential decay and emission characteristics. So superradiance and superfluorescence is characterized by a delayed emission. And this was observed for the first time in '73 in a dense ensemble of dense and long ensemble of atoms. You see here this intensity profile as a function of time. You have a delayed emission and a peaked emission. This emission peak, it's a very strong peak. It scales with the number of atoms in the sample squared. So it scales quadratically. And it fluctuates from shot to shot. So this delay time, also this peak, and this intensity profiles fluctuate from shot to shot. And that's a manifestation of quantum fluctuations on a macroscopic level. And that was one of the reasons why quantum people dealing with quantum optics were very interested in this phenomenon, because of this macroscopic manifestation of quantum fluctuations. The theoretical descriptions, theoretically it's quite a tough problem, especially if one goes to optically thick samples where the propagation of the field needs to be taken into account. And these theoretical descriptions have been mainly based on Maxwell-Bloch equations. So these are, for two-level atoms, one would treat the atomic system as optical Bloch equations, describing the density matrix of the atomic system, and coupled these equations to the Maxwell equation for the propagation of light. And in order to account for the quantum fluctuations and initiate this decay process, one either would choose statistical initial conditions in the density matrix, that's the so-called tipping angle approach, or one would use phenomenological noise terms added to the Maxwell's equation or the Bloch equations. And we then realized by looking into the details of that actually these Maxwell-Bloch equations with these phenomenological noise terms they don't describe this transition from spontaneous emission to amplified spontaneous emission to superradiance correctly. One needs basically to go beyond this tipping angle approach, this statistical initial condition approach, because in real experiments, one needs to treat the pump process. Whereas in most of the theoretical treatments, one kind of assumes that one has an ensemble of states already in a certain prepared initial state. And we wanted to really look into the complex pump process to prepare this occupation inverted state in the systems. So for the first method we developed is for a two-level atom, and we start out in the usual way. We treat this two-level atom by matrices that are corresponding to the population inversion in the system and the coherence of the density matrix or the transition operators. And we look into the electromagnetic field is quantized by the usual quantization procedure, treating many different modes. The atom field interaction Hamiltonian is the usual minimal coupling Hamiltonian in dipole approximation. I don't know, I cannot. Okay. Sorry, I couldn't forward my slides. So then we start out to formulate the operator equation. So the Heisenberg equation of motion for these operators, for the sigma operators and the bosonic operators for the field, and formally integrate the expression to get an expression of the time-dependent field operator. And here you see, this formal integration, you get a coupling to the radiation by the atoms. And you are left out with this operator, annihilation operator at time 0, and that's the operator that will account for quantum fluctuations. And then having this field evolution of the operators, you then can formulate the operator equations for the atomic subsystems, so for the population inversion and for the coherences. And one sees that one has terms that still have contributions of this annihilation operator of the fields. These are the so-called Langevin terms. And these are the terms that are capturing the quantum noise that initiates the process. I'm not sure what happens with my slideshow. I cannot. It always jumps around. Sorry for that. And now it's back.
It may be playing automatically time slides. So if you exit this display mode.
Yeah, I don't know. It was kind of swiping with my mouse, so I don't know.
Oh, okay.
Okay. So this is these are the equations for this Heisenberg-Langevin for the operator equations. And now we are aiming towards getting a mean field description of the system. This means that we would like to recover, the mean irradiated intensity as a function of time, and the mean, the averaged spectral properties of the immediate radiation. So in order to do that, what we need to do is to calculate the mean values of certain correlation functions of the system. So for instance, we are looking into, an equation of motion of the correlation function that measures the coherences of atoms at different spaces points in time in space. So we have here this quantity here is the coherence of atom A correlated to the coherence of atom B at the same point in time. So this quantity then will directly relate to the irradiated intensity of the emission. So out of this quantity, we can calculate the vector potential of the field. And the evolution of this expectation value is given by this equation. And it's almost a closed set of equation, but one actually sees here that here a 3 operator average, ensemble average comes into play. So one in principle, one doesn't get a closed system of equations. One would now need to formulate the time dependence of this triple product correlation function. But here now we approximate this correlation function by a factorization and factorize it in 2 terms. So that's quite a critical step in this approximation. And we will see further that this works well for the 2-level atom, but brings along problems for n-level atoms. One can then also go to a continuous description of the medium by not looking into particular atoms A and B, but really performing a swept coarse-grained average over space. Then one gets a function that counts for the population inversion in continuous function as a function of Z, position and time, and a correlation function of the coherences. And these are the resulting equations one can then solve completely deterministically for the occupation inversion and the correlation function. Here we have the radiative coupling terms to other atoms involved. That's sort of follows causally the emission of all the other atoms. And we have here source term for spontaneous emission. And if one gets these quantities, one can then directly calculate the intensity as a function of space and time. And for the spectrum, the immediate spectrum, one needs another correlation function. Via Wiener-Khinchin theorem, we need the correlation function of the potential, the vector potential at different points in time. So we get another equation that we can solve once we have solved the equations of the atomic system and calculate the spectral features of the emitted radiation. So this is this theory presented is quite ideal because we have not treated the pump process yet and decoherence processes. The pump processes can be quite involved, and I am showing here the case for our experiment on xenon atoms, where we started out from xenon in the ground state. This state would be ionized by the FeL to the 4D whole state of the xenon ion. These states would decay via Auger decay to a set of states in the decationic ion. And these same states can also be occupied by direct valence double ionization pathways. So all these pumping processes need to be accounted for in order to really get a quantitative description of the process of emission. And we do this by rate equation approaches. And in the case of clusters, we need to also treat for decoherence effects. And this is technically done by introducing into the Liouville phenomenon equation a Lindblad superoperator acting on the density matrix. And here you can see the Lindblad superoperator for a typical decoherence with a rate gamma here. And as you would expect, I mean, from phenomenological theories, typically, what this Lindbladian actually results into is that this correlation function, they do not then decay via the spontaneous decay rate, but by the total decoherence rate, which is the sum over the spontaneous and the decoherence rate. So this is the formal explanation or derivation why we can kind of introduce this total dephasing or decay rates in the system. So now if we solve this system of equations then numerically, here for ideally pumped systems, we can get, for instance, the temporal intensity profiles of the emission and the spectral, the spectrum of the emission as a function of different interaction length in the systems. So we can walk into through different regions in this elongated system, or increase the length, the optical length of the system, and then follow the emission features. So for very optically thin samples, we recover spontaneous emission. You see here an exponential decay and an intensity profile that's exponential. In the spectral domain, we get a Lorentzian with the width corresponding to the spontaneous lifetime width of the transition. If we go into longer samples, if we increase the optical density in the sample, we then see that at later, points, we have emission that is delayed in time. And so we have the super radiant emission. The total emission yield, here that's shown here, as a function of propagation distance is increasing, not quite exponential, it's sub-exponential increase, but increases over many orders of magnitude. So we get all this amplification behavior. And if we have very saturated emission, for very long samples, we get this typical ringing phenomenon of superradiance reflected in this kind of peaked structure in the emission. So now if we include dephasing, we see the phenomenon of amplified spontaneous emission initially. So we have a much broader emission width that's given by the total decoherence time. And then, the system starts to amplify. This amplified spontaneous emission amplifies exponentially. And in this exponential phase, one actually sees gain narrowing, meaning that the spectrum is getting narrower and narrower. And at some point, one then transitions to the scheme of superfluorescence, where one again can have this ringing phenomenon. And so even in that case, at some point, coherent pulses are created. And we can then really also include the pumping processes and compare quantitatively to our experiments. And here is shown typical gain curves, meaning the collected number of phonons as a function of pulse energy or as a function of pressure of the gas medium. And you see that, I mean, we can almost quantitatively describe with a theory the experimental findings. And we have experimentally also measured an increase of the width of the emission that also can be recovered by a theory and supports assumption that we have superfluorescence observed in these xenon emission experiments. So we have had recent experiments based on liquid phase manganese salts in solution in water, and we are in the future planning for realizing an X-ray laser oscillator. This is a project in collaboration with Claudio Pellegrini and Uwe Bergmann from LCLS. And here we need to treat at least 8-level system or generalized n-level system in looking into the emission, the superradiant emission of kappa K alpha on the kappa K alpha transitions. And you see that you have 2 degenerate K-shell levels and 8 final state levels of the different fine structure components in kappa. So the question is, can we use this correlation function approach? And we can immediately, immediately we came up with a 3-level system that showed that this correlation function approach breaks down. So if you consider this degenerate lambda system where you have 2 degenerate ground states of with orthogonal coupling matrix elements to this excited state, you see that you actually need to treat 3 operator correlation functions and even 4 operator correlation functions in this treatment. So for the 4 operator correlation functions, we were quite confident in just splitting them up in factorizing them. But if you actually try to factorize this 3 operator correlation function, you see that due to the symmetry reasons, for this particular example, you see that this correlation function would, in this approximation, be 0. And if you then solve for these mean field equations, what you actually see is that you observe occupations of the excited state that are negative. So completely unphysical results, and that show that the system breaks down. And for n-level systems, I mean, you run into similar problems, and a quantitative description of the emission is no longer possible. So one needs to go to a different approach. And so we opted to derive stochastic differential equations that are based on Fokker-Planck equations one can derive for this system. I'm not sure if you're familiar or still remember your quantum optics courses. I mean, typically, Fokker-Planck equations might have been covered there. One starts out with the Liouville phenomenon equations with Lindblad operators, and that governs the dynamics of the system. And then one chooses a representation of the density matrix of the complete system. In the case of superfluorescence, this means we need to treat the combined systems of field and atoms. And we do this by generalized Glauber P function and by representation of this density matrix by coherent states. So this would be, I mean, the first approach one tries, because that's the typical standard approach in quantum optics, to represent the density matrix by a coherent state representation. It turns out that this presentation actually does not work for the case of superfluorescence. The resulting stochastic differential equations we get there are completely diverging. We cannot even describe the decay of a single atom in this case, let alone a superradiant peak. One would need to average over many trajectories. I mean, basically a convergence of this sampling is very difficult. So we introduced a novel representation of this density matrix. And this representation comes along with a second quantization in Liouville space. So that's a quite novel concept that we introduce. We are about publishing a paper on that quantization approach. It's, I mean, you know, second quantization in Hilbert space, but here now we need to quantize Liouville space, the space of the density matrix. That's formally done by introducing creation and annihilation operators with two indices. And it will turn out that these trajectories, or this, I mean, that will be come out of this stochastic trajectory approach, that this kind of annihilation operators will play the role of the density matrix, the atomic density matrix. As operators, you can think, I mean, if you have a large ensemble of atoms in a specific region, by this creation operator, we can either create a population or a coherence at this specific site. So you can somehow count correlations and occupations of different atoms. Formally, we then introduce a representation of the density matrix by a quasi-probability function that's made out of a distribution of delta functions in these operators. And I mean, we can then in this way derive equations, the equation of motion for this quasi-probability function, which has the form of a usual Fokker-Planck equation. I mean, it's written here quite nicely with a partial derivative of xi. You need to know that xi is basically an n-dimensional trajectory where we cover all the different field modes and atoms in the system. So it's actually quite involved. But nevertheless, I mean, formally then we can solve this evolution of this probabilistic distribution function by sampling trajectories. This is given by a classical part of this trajectory and quantum noise part that sort of recovers the quantum properties of the field. And then we can create, I mean, the average, I mean, the expectation value of the density matrix is then just recovered by averaging over these trajectories. So that's the equations in compact form. One can then also rewrite them in a form that sort of then shows is closer to the observables and to the physical properties we actually know. We need to define initial conditions for the bosonic operators and for these trajectories. So we suppose that we initially have no correlations of the atoms in the different regions, and suppose that we have all atoms in an excited state initially. And then one sees that this quantity B that's related to the annihilation operator is actually nothing can be interpreted as a density matrix of the system, and we end up with equations that are very similar to the Maxwell-Bloch equations, but now with noise terms, with derived noise terms that have well-defined statistical properties and that recover the quantumness of the system. So we have here this evolution of the density matrix then that's given by this kind of density matrix, that's given by terms that describe pumping, dephasing, and spontaneous emission. The interaction with the field, here it is the vector potential of the field, and features these quantum properties. We have then also an equation, I mean, for the currents that create the fields, and the noise terms between in these currents and in this simple density matrix description, they are correlated. I mean, so you see that that's the kind of correlation of the noise properties we need to realize. And we actually, I mean, it's more an art than real that we can give a really good description how to get these noise representations. But for large number of atoms in the systems, for n larger than one, much larger than one, we really can solve these stochastic differential equations, and they turn out to be stable. And here I'm showing you first results of kappa on the kappa k alpha transmission in this 8 level atomic system. You see here, for instance, populations, the average populations of these 2 states, final states, averaged over 100 runs. I mean, at some point they should converge to one line, so they should be equal by symmetry reasons. So you see that we are not quite yet converged, and the coherence. The coherence, I mean, it's reflected. I mean, for a single trajectory is actually quite large and reflects the emission of the superradiant emission. But on average, I mean, the coherence has to be 0. So this is a kind of a convergence check for the trajectories you would for your trajectory ensemble trajectory approach. We can then also get single trajectories for the temporal emission profiles or average temporal emission profiles and the spectrum. And I would just like to mention that this kind of trajectory approach is very appealing because if we have the stochastic trajectories, we can calculate higher order correlation functions of the immediate fields and distribution functions of the field properties that we can directly compare to the experiment. For instance, in the experiment, we have here the number of photons compared as a function of Pulse energy. And if one looks experimentally in the distribution of photon numbers at a given Pulse energy, one sees that this distribution changes quite dramatically from exponential decay-like to a kind of log normal distribution or something. So I mean, we can now we have a theoretical means of really predicting these distributions now by this trajectory approach. So as a summary, I introduced a mean field approach to treat superfluorescence by coming up with the equation of motions for the 2-point correlation functions of atomic coherences. It works well for 2-level systems, but in order to treat these systems, I mean, in a computational tractable way, one needs to factorize 3 and higher order correlation functions, and this factorization is no longer possible for n-level systems. So we introduced a new stochastic differential equations approach. We could show, I mean, that is introduced based on a novel second quantization procedure of Liouville space. We basically derived stochastic differential equations. We are successful in constructing the appropriate noise terms for these differential equations and showed first successful application to the kappa k alpha emission. I mean, for 0D, for the 0D case, meaning that we did not treat any propagation of the fields yet. And in the future, we are going to implement this stochastic differential equation approach into 3 dimensions. And the first application will be really a project that's planned at LCLS to realize the first X-ray laser oscillator. And with this, I thank you for your attention, and I'm open for questions.
Okay, thank you very much, Nina. That was really fascinating stuff. So we're up to 84 people attending who can ask questions. So as discussed at the start, if you have a question, you can use the raise hand functionality on Zoom. in which case we can enable your microphone and camera to ask a question in person, or you can simply type a question into the question and answer sort of text entry part there. So Henry is going to keep an eye out for anybody who's raising a hand. And while we're waiting for the first question from the audience, perhaps I can ask, so in terms of this outlook, in sort of extending this method that you've described, you mentioned the propagation effect. I mean, how much work is there to extend to look at the propagation effects, and is that sort of built into this three-dimensional method you're proposing to?
It's numerically going to be very challenging. So I mean, it's numerically challenging, and then the big question is if the noise dams will remain stable in this approach. So I mean, we have to develop a new strategy. I mean, how to do a numerical, I mean, full approach. You know, even on the scale of the Maxwell-Bloch equations, it's quite difficult because it's a multi-scale approach. One needs to cover basically we have propagation distances in the experiments up to a few millimeters, and one covers a field amplification over 8 to 9 orders of magnitude in these 3 millimeters, and one has to treat quantum noise at the same property. So it's quite it will be quite challenging.
Okay.
I mean, also for the noise operators, I mean, to construct the noise, no? I mean, for this simple system, this 8-level system in copper, this model system, we need something, we have noise matrices of 200 by 20. I mean, the matrices are really huge. And we have 64 density matrix elements. And I mean, couple of, the equations I showed were very complex, compact in the way we wrote them down, but I mean, there are a lot of coupled differential equations, and to really come up with a stable representation and with this noise is difficult. One has a certain gauge freedom in this noise, so the only thing one has to reproduce are these second order correlation functions of the different noise terms. That's the boundary conditions, but within these boundary conditions one can play around with choosing different realizations, and different realizations turn out to be stable or unstable in the numerical implementation. And that's something we want to understand in the future. And we also have a collaboration with an applied mathematician here that will start soon in order to look into that from a mathematical point of view.
If your matrices get any bigger, then we're dangerously close to it being an HPC question, a high performance computing question, which starts to pique my interest. Okay.
We will run into that for sure if you want to have a full 3D description of the process.